Welcome to a short video from the designers here at BitWise Laboratories. These videos are intended to give you a quick introduction to our instruments to help you understand what they can do, as well as let you see them in action. The STEPScope is a compact, high-performance instrument that performs time-domain reflection and transmission measurements. Using its built-in fast pulsar, the STEPScope can measure impedance on single-ended or differential transmission lines. Waveforms can be viewed, panned, and zoomed, and exported, helping your efforts to characterize a cable, a PCB, or a component in your lab. Let's start our tour by looking at a block diagram. Here we see the major elements inside the STEPScope. For example, we see how the internal pulsar is coupled directly to the sampler using a resistive power summing element. Fast pulses leave the pulsar and is sent both to the internal sampler and to the user's device under test. This becomes the incident pulse for your measurements. Any deviation in impedance that this edge sees will cause some energy to be reflected back to the STEPScope, and with the appropriate time delay, it will reach the sampler and become part of the sampled waveform. The STEPScope processes these waveforms along with waveforms taken during calibration steps to compute the ratio of energy that was reflected, and then translates this back to impedance versus time display. The STEPScope also includes a finely calibrated time base to allow waveform sampling at sub-picosecond resolutions. Time-based information can also be sent out the STEPScope to another STEPScope to allow coordinating two STEPScopes to work together. This is needed, for example, when we want to perform time-domain transmission (TDT) measurements. In this application, the pulsar of one STEPScope outputs the fast pulse, which then travels through the system under test and back into the second STEPScope. The sampler in the second STEPScope is used to measure the transmitted waveform. Different transmitted waveforms can be compared to each other in both the time domain and frequency domain to make transmission and insertion loss measurements. The processor inside the STEPScope is running Linux and hosts both user and remote control interfaces. The user interface is done using a web server, allowing multiple users to connect to the STEPScope using any web browser. The remote interface uses a TCP/IP socket to implement familiar Skippy-like commands using simple ASCII text. While it's possible to connect a monitor and keyboard and mouse directly to the STEPScope and access the user interface using a browser on the internal desktop, most customers access the STEPScope over the Ethernet network. Finally, the STEPScope also includes two ADC-generated voltage outputs. This is suitable for sourcing and syncing about 50 milliamps of current. You can set these signals to programmable voltages and use the outputs for bias generators or threshold voltages to help with your test setup. In today's demonstration, I'm going to make simple measurements of a device under test. This is a synthetic example that I just created from something in my lab. We will send the pulse out single-ended, thereby terminating the other differential output, and bring that signal through a small transmission line, an exposed wire, and another transmission line back into a termination, just so that we can see and experiment with the kinds of impedance mismatches we might see in a real circuit. The first thing we're going to need to do is get connected to the STEPScope. For that, I'm going to bring up a browser here. This happens to be Google Chrome, but you could use other browsers. To find the IP address of the device that I'm connected to, sometimes we can, if names are served directly from your local area network, we can just use the name of the STEPScope device with its serial number. Otherwise, we can use the lookup feature that's present right in the STEPScope. For example, if I reach over and press the button at the back of the STEPScope, then I can use this lookup local device, and I can type in the serial number 003005 of my device, and it will actually show me the IP address of the STEPScope that I want to use. If I click directly on this, then it will link directly to the STEPScope and bring me to its website. Right now, this STEPScope has terminators on both outputs, and I can bring up its step response and ask to align the step response to the 0101 part of its transition. And I can see the step that I'm generating and the response to that step that I'm seeing. Before I get too deep into the measurements, perhaps a quick introduction to the user interface is helpful. The BitWise STEPScope has a few different segments of the display. For example, down below we have some status and control. For example, I can adjust my pulsar amplitude and how often for the pulsar to generate. I can also use a remote pulsar. If I'm using two devices, I would set the IP address of the second pulsar here, and then through one device I can control both. I can set the general purpose I/O voltages, perform platform calibrations. Those are all functions that I access directly here on the bottom bar. On the right, I have my different analysis views. Today we're going to be looking at the step response and the TDR. Later on we'll do other videos on both TDT and return loss. Up above there's a menu here where we can get access to resetting the user interface, passwords to lock the user interface, resetting the factory settings. Those can all be accessed directly right here. The run and single and clear buttons are common through all the analysis. For example, if I rerun this display, it will go run, and down below here you can see it's constantly making new measurements. I might also just say run a single, in which case I'll get a single measurement made here. It's typical in each of the different analysis techniques to support some tools. For example, if I click this icon here, I can get to cursors. For example, I'll just hit fit cursors, and that allows me to move my cursors around, for example, and make direct measurements. Down below here, I have access to some of the parameters. For example, the number of samples I'm taking in my waveform right now is 1,000. I could change that measurement right here. It also shows me the effective sample rate. One of the common questions that comes up always on a TDR instrument is to understand in detail the pulsar itself. Let me go ahead and use this to do that. For example, if I move my pulsar here to the beginning of my pulse, I could look at the rising edge or the falling edge. For example, let's look at the falling edge. And I can see that around 44,213 nanoseconds. If I set that in as my time offset, 44,213, and maybe a time span of 1,000 picoseconds, sorry, it was picoseconds that I was referring to, then I should be able to zoom in on this. I can also use my click and drag features. For example, if I say X scaling, I can just grab the chart and move it. Then I would be able, and when I pause, by the way, it reassigns all the 1,000 points that I wanted to capture to the zoom level that I'm interested in. If I was to use X panning and move that back over, you'll see it will recapture and get even more data. If I go back into zooming and zoom in even farther detail, we can continue the capture. And so, for example, let me fit my cursors. I'm going to sort of estimate 1090, something like that. I can move my cursors in time here and here. and there's 17.8 or so picosecond fall time. You can also see the resolution inside of the sampler when it starts to stair step in here a little bit. That's real, and that does happen, but again, this is assigning 1,000 points right now to this view that's only 1,000 points to a 66 picosecond view. I'm getting very fine resolution in this sampler. But again, I can auto-align to see my entire pulse being transmitted. This is the pulse of my signal going out. We can see small reflections that are coming back, and we can see the repetition rate of this pulsar. The repetition rate of the pulsar is adjustable here with this pulse width setting. For example, if you're measuring short cables or short distances, you might set this to a fast pulsar. But if you have to look at very long reflections, of course, then this pulsar would want it to be much more spaced out. Longer pulsars take more time to capture their waveforms. So that's the trade-off you'd make. Another nice feature that you will find in many of the analysis techniques is up here. For example, this is to download a CSV file. If I click this button, I will get my waveform file here. For example, this would capture my data in a CSV file format that I can easily export and use for other analysis. Okay, so the next thing we want to do is look at the TDR response of our device under test. I'm going to press the TDR button, and the first thing I need to do is perform calibrations that define the reference plane of my TDR. If I click down here, I have these two calibrations that have to be run: calibrating a short and calibrating a termination. For example, if I press calibrate a short, it instructs me that I should screw a short on at my reference plane, which I'm doing right now, and I'll press the OK button, and it will go about measuring the waveform that's reflected from this short so they can use it later on when it does its computation. Then it's ready for the termination calibration. So I'm going to unscrew the short and put on a reference termination and calibrate the termination. Press OK to this, and now that will measure my termination waveform. Again, that waveform is used when computing impedance coefficient, or the reflection coefficients, to get to impedance. Once I'm done getting my calibrated waveforms in, then I can screw on my device under test, which I did, and up here I can reset my chart view to the time elements that start at my reference plane, and run one waveform, for example, and it will show me my reflected waveform. Let me go ahead and make that a little bit larger. We can see time 0 is the start of my reference plane, and I have some response here, and then a long area. So clearly on my pulsar, and I'm collecting data far longer than I need to, but I can use my zooming capabilities, for example, to X scale and zoom this out. Now when I let go, it'll use all 1,000 points right at that point, that area, and get me much nicer detail. I can zoom in the vertical axis to get more data as well, or more gain. And let me get that into my view right here. And now I'm ready to make some measurements. I can turn on my cursors. Let's fit the cursors so that all 4 cursors are present. And for example, here's where I can see my launch was at 50 ohms, but my PCB trace is probably 51, a little high, not unlike the termination that was screwed on at the end, but clearly there are some inductive spikes here, and up to 58, 59 ohms, and some capacitive dips, as well as capacitive dips through the connector. Inflections that are above the nominal impedance are inductive, and those below are capacitive. Similarly, I can make time measurements by finding something I might be interested in, a feature in time, and maybe to another location. This is 114 picoseconds from here to here. Remember, this is a reflected measurement, so the actual transmission time was half that, because this would be a return trip. So this would be half that time. Again, like all our graphs, we could come in here and press the download, and I can have my data readily available in a CSV file for analysis in other tools. Let me continue to zoom in a little bit in the time axis here, just so that I could see into this board a little better. And just for fun, I will put my finger on the trace. You can see this is me moving down that trace. Recall what this board looks like. I am moving down this trace a little bit here. Move that up. And as I continue to move down the trace, I am measuring different impedance. As I finally get to the exposed wire that is pressing here, the first one is this inductive spike. This capacitive spike would be right here, while the wire runs right over a ground plane and is only separated by a thin piece of tape. And then as I continue on the other side of the device, I can see other impedance loss on the output trace down here, to the point where I finally get to the output signal. The fast updating speeds that we're seeing here include already averaged waveforms. So there's no need to turn on large numbers of averaging, something that we used to always have to do using sampling oscilloscopes to get fine measurements, because of the way this waveform is sampled. So this has been a quick introduction to a simple measurement of a real device under test, where we're measuring impedance going along a line. This exact same principle would apply to cables or cable testing. One can see how easy it is to make a delay measurement. For example, if we want to know the length of a trace, we can find that out to very fine detail by tracking an edge that's on two different waveforms. Thank you for watching. We hope this quick introduction helps you understand what the STEPScope can do and how to use it. We know there will be a learning curve as you come up to speed making your own measurements, and we're here and ready to answer your questions so you can get the most out of STEPScope.